Welcome to Team A959's presentation of the completed mass transit simulation. Our group convened early on Canvas for a head count to discuss what roles each member would like to tackle. After sharing our coursework with one another, we selected Cooper's work as the foundation for the project going forward, as he had had the highest overall marks for both the UML and the working code demo. Eduardo set up a GitHub account for code sharing and volunteered to kick off the UI work. Michael Thompson volunteered to do the UML. I took on the task of owning the presentation. Ankit Roy never showed up. Per the earlier client requests, the application we used as our foundation for further work was able to accurately predict when buses would arrive at given destinations, providing a CSV that contains instructions telling the system what routes make up the road network, the stops that make up those routes, and in what order they come, what buses follow which routes, and finally, instructions for where those buses start. Foremost among the new requirements was to create a UI for our users to interact with this model. At its highest level, the application consists of two parts, separated by concerns. A UI application written in TypeScript using Angular 2 that allows the client to interact with simulations and run alternate tests, and a backend application for handling the business logic of the simulation into which a Spring Boot REST API has been baked that exposes endpoints of the core application to the UI. With Spring Boot in place, the backend was augmented with an additional class, MTS Controller, which maps the requests paths made by the Angular app to the other parts of the backend application. The former main class was renamed MTS Service to reflect the new architectural concern of the business logic being hosted as a Spring Boot service. Clicking on various elements in the UI, such as the new event button, causes Angular to send HTTP requests to the backend. The next significant functional enhancement was to actually model how the bus's schedule influences the flow of riders from their departure stop to their destination stop. To this end, the simulation functionality was extended to handle a second configuration file that provides data about the range of passengers that can be expected to take a bus from a certain stop to another at a given time of the day. Our UI provides inputs for the user to upload CSV instructions determining the initial system state. Buttons for allowing the client to play through the entire simulation or advance chronologically through the discrete events of the simulation forecasts are found above. Once a user uploads the scenario configuration file and the rider probability configuration file and runs the simulation, the table below outputs in sequence what buses will arrive at what stops and when, and how the passengers on those buses and at those stops will behave as a consequence, by either dismounting at the stop, boarding the bus, or mating on the respective bus or stop. Using another configuration file showing the rider distributions at another time of the day, our simulation forecasts how those riders will be transported instead. Restarting the simulation with a new setup file for how many riders use the system at a given time of day is useful for demonstrating known issues with the mass transit system we are modeling, but it doesn't provide much in the way for how to solve the problems it reveals. The new requirements for the system amount to tooling to make it useful. 1. To provide a means for the system to be wound back in time so that 2. Variable conditions in the state of the system mid-simulation can be run, thus demonstrating how well it performs under those modified conditions, and allowing for comparison to the previously run simulation. By selecting a number of steps to rewind and clicking replay, the state of the system depicted in the table below should be updated to reflect the state of the system that many steps ago. Here we can see the system executing 10 events synchronously. Following that is an example where the simulation runs 10 events, then rewinds 3 times, runs an event, rewinds 2 times, runs another event, and rewinds once more before executing another event. Rewind functionality is performed by the System Utility class, which stores complete snapshots of the simulation state at a given point in time. Rewinding amounts to resetting the system state to the data contained in the snapshot for the time requested, which is then assigned to the new system utility in the main function. Unfortunately, we weren't able to capture in code all that was outlined in the UML for our system. Use case diagram probably shows most clearly at a high level what those other functions were, namely being able to change the system variables to see how it impacts the system efficiency, and quantifying that with a calculation. That concludes our presentation of A959's final project for the fall semester of Georgia Tech's Software Architecture and Design course. Thank you for watching.